Hi, my name is Jim, and today's topic is pulse waveforms, which are different than anything that we've seen thus far in the course. And the circuit we're going to be using looks like this, and you're going to be seeing that has other functions in other circuits. And what's on the board here has to do with being a base cut circuit for audio. And we need not concern ourselves anymore with this, because this will be covered in the future. But do note that the collection of parts, even though the circuit looks the same, can have very, very different meanings from the standpoint of what the circuit designer is attempting to do. And that's the whole point of this. What we're going to start with is a DC source to explain what happens in this circuit, and just ignore all of this because it's what would be used if we were using a circuit in a low-pass configuration. So this is the situation here, is we're starting out with the capacitor voltage equaling 0 volts, and you absolutely must be told that. And we're going to close the switch here, and when we do that, we're going to have current that's going to charge the capacitor, and the time it takes to do that is referred to as the time constant. Now, the time constant, tau, or just a symbol, in an RC circuit is equal to R times C, and if we have an LR circuit, it would be equal to L divided by R. So the smaller R becomes, the longer it takes the magnetic field around L to collapse. Now, we're not going to address this because inductors used in circuits aren't really too desirable unless you're in a switch mode power supply. And the reason is they're costly. They have to be wound. They take up more board space, and they're subject to interference because, well, they're a coil wire, otherwise known as an antenna. They radiate energy. It can be near field or far field, meaning near, or flux returning is near field. That which does not return is a radio wave. Okay. Anyway, so we're going to be focusing on RC time constants. So this is the general thought of this, and how do we define a time constant? What is it? Well, if we start, what we see is that if we go to charge a capacitor and we flip the switch, it's charging up toward the final voltage, which in this case would be 10 volts. And this is an asymptote, so it really never gets to 10 volts. But the industry says after 5 time constants, it's considered to be fully charged. So the voltage over here somewhere would be 9.99 and so forth. So if we multiply our R and C together, what we end up with is 2.2 milliseconds. And that's going to be the time constant of our circuit. So the definition of a time constant is that at T0 plus, which means a super infinitely small instant after the switch is closed, the capacitor is going to start to charge. And what is the rate of change of this? Now, slope is equal to rise over run is equal to m, just like what we learned before. And in calculus notation, if we take a look at that, and when we use a delta V over delta T, as you kind of think of measuring a small voltage and dividing it by the associated time, but that gives us an approximate answer. So I made this up, I don't think you'll find it in any book, is that the slope equals the limit as delta T goes to 0 of delta V over delta T equals the calculus notation of dV dt. And that produces an exact answer, where this will always be off by a little bit because you can't have the delta T as 0. So undefined. So anyway, getting back to this, if we take the initial slope of this and project it until it hits the final voltage, and then drop that down, that's the definition of a time constant. 1 tau, 2.2 milliseconds, 2 tau, 4.4 milliseconds, and so forth. So it's kind of good to know that. The other thing is, at 1 time constant, the capacitor is approximately 63% charged. At the second time constant, the difference between where it started and where it's going to end is 63%. So every time constant, the capacitor charge is going to move 63% relative to the previous time constant closer to the final voltage, which is 10 volts. So that's kind of a nice thought because it allows you to do common sense error checking based upon that. So this is just about how they define a time constant, and other than that, it's not useful for what we're going to be using. Our methods don't need to know this, but that's the background behind it. So why do we need to do this? Well, let's take a look at a microcontroller, and this is an active low reset pin. So when we apply 3.3 volts to power this, what that looks like is a step voltage, and then this pin will asymptotically charge to our 3.3 volts. Now, the reason that we're waiting here, and that would be this time, is there's stuff that has to go on inside of a microcontroller before it can start to execute code. For example, a charge pump has to set the whole block of silicon that this thing is laying on down to about negative 0.7 volts. Otherwise, the transistors won't work. Further, registers have to be initialized in here. For example, the program counter or instruction pointer has to be set to the first instruction in the program. Makes sense? And it takes time to do that. So we apply power here. The manufacturer determines that it's okay to start to execute at some point, and then it does its internal initialization to get ready to execute code. Modern products don't do this. They save parts by some software thing inside. They take care of that delay. But anyway, that would be kind of a good example where doing this. Once designed a little display using a controller to drive a laser. Pick it up on a photocell and display the result. And I had the laser, the bit rate very slow so students could see this pulse. And when I fired this up, the controller wouldn't work. Then I read the data sheet and learned that my time constant was way too small. Proc couldn't initialize. Fix that, all is well. I guess the message is it pays to read data sheets. Okay, let's talk about some equations here. And we're going to start with our circuit again, and I redraw this many times. And I'm going to define I flowing in this direction, and once again VC initial equals 0 volts. As we close the switch, we see it asymptotically approaching our supply voltage, and the equation to do this is that the capacitor voltage equals the source voltage times the quantity 1 minus E raised to the negative time divided by the time constant, R times C, and sometimes you see that written as tau. So putting this in common sense terms, as e to the negative x, as we saw before, using x here, as t gets larger, this term gets smaller. And we're subtracting a smaller term from 1. And at 5 time constants or more, essentially what's in parentheses is equal to 1, and the capacitor voltage is equal, almost, to Vs, as we see here. So for a charging capacitor, this is the guy you want to use with the 1 in front of it. Okay, so yeah, just remember this term goes to 0 as t gets bigger. And if you want to see this and you have a graphing calculator, it's very easy to do. Just pick a voltage and, pick a time constant, and you'll see that. Now, for the heck of it, I decided to graph e to the negative x just to refresh myself on, what e looks like, raised to a negative and to a positive power. So, in green here, we see a calculator plot of e to the negative x, and what we're going to be working here is in quadrant 1, and what I see and expect to see is e raised to the 0 power is equal to 1. And then as x gets smaller and smaller, meaning larger time, but it was multiplied by negative 1, the term goes to 0. So that's a decaying component of this, and we're starting here at 0. We're not going to be over on the negative side in quadrants 2 and 3. So if I were to say multiply E by 3, I wonder what that would look like. And all we do here is we start out at 3, and this extends out further, as we would expect it to do, because we're multiplying the value e to the negative x, whatever that is, by 3. So those would be what that would look like in the first quadrant, and that's what we're going to be working with. So we're going to be working with pulse waveforms, as I said, and these are going to be unipolar, which would be kind of like a clock voltage that you've seen before, and then we're going to move into bipolar. And this is a perfect square wave, and in a perfect square wave it's non-continuous. It's quite different than a sine wave. When we reach a point here where we have a slope of undefined, and this means that the rise time is 0 seconds. So we can't deal with an undefined slope, so mathematically this looks like a little cup and that looks like a little dot, and they occur at the same time. It's just at different voltages. Some books have this as a dot and this is a cup, same meaning. So in a perfect square wave is what we see is that the rise and fall times are 0 seconds, and the waveform would be looking like this. So what that as an inference to is that we can't analyze anything with a square wave completely at one time. So we have to break it into pieces, and that's called piecewise linear. And we analyze this piece and then this piece, and if we need to, this piece, and so forth. So we can't do it all at the same time. So if we want the exact M, and I made this up, I don't think you'll find it in a book anywhere, but the exact slope would be equal to the limit as t goes to 0 of delta V over delta t. Now, we've seen this before, and what we typically do is make a small measurement of V and a corresponding measurement of t, and then from that we conclude what the slope is, and that slope may equal conductance or resistance or whatever. But if we do this, what we end up with is an exact M. So that would be corresponding to the dV dt on the previous page. And exact is sometimes very important. So that's a perfect square wave. We're not going to see that. And this is a real square wave where I'm showing the rise and fall times here, and even though this looks to be vertical, it isn't. And we're dealing here with a square wave source, unipolar again, only goes in one direction. And what we're seeing here is that it, starting out here at t0 plus, which is a super small instant at a time when this goes high, is that the capacitor will start to charge toward the final voltage here, which is V. So industry standard says 5 time constants later is considered to be fully charged. Now, for us to do this, there's a certain restraint, and that means that the period divided by 2 has to be greater than or equal to 5 tau, or it'll never get close to V. So period t in a periodic waveform is the time it takes for the waveform to repeat itself, and t over 2 is going to be our chunks here that we're going to be analyzing. So that's what we have to do here, is keep in mind that 5 tau is enough time for that cap to completely charge or discharge, and this is a requirement for that to happen. Now this page, again, we're starting with 0 volts on the capacitor, and this may look pretty bad, and there's a lot of writing here, but this is going to be number 1 and this is going to be number 2, and when we do the calculations we'll be referring to each. 5 tau equals 11 milliseconds, and then I'm starting over again, so instead of this being 22 milliseconds, it's 5 milliseconds for this piece. I'm defining the current flow in this second, and tau, the time constant, R times C, is equal to 2.2 milliseconds. So our equations for charging are this: VC equals the source voltage Vs times 1 minus e to the negative t over RC, and remember that that value gets smaller and smaller as t gets larger and larger. And for the discharging waveform, it's a little bit simpler. Is VC equals VC initial, and in that case this is going to be 10 volts right there, and it's going to be multiplied by a decaying exponential, giving us a voltage which drops back down to 0, and then we repeat again with this guy and repeat again with this guy. So equations aren't too bad, just have to look at them and know what they mean. So, for an example, VC initial equals 0 volts, telling you that. Find VC at 3 milliseconds. Okay, easy enough. VC equals our starting voltage, 10 volts. Here's our equation. Negative 3 divided by 2.2 milliseconds comes out to be 7.44 volts. So if I take a look at this and try to graph it at 3 milliseconds, and that's 2.2 milliseconds there, the time constant, and projecting up and across, comes out to be 7.44 volts, with all due respect to my artistic ability. So that would be one definition. And if we discharge, and this is going to be number 2 here, our mission is to find VC at 1 millisecond. So our equation would be VC equals VC start, and that would be 10 volts times the decaying exponential, and that would give us 6.34 volts, which would be right about here. So these two equations allow us to find VC at any point in time, and the reason we might want to do that is if we're interested in designing a clock. We can't have a threshold where it upticks a second. We need 2 points, so a noise burst here won't cause the clock to gain time. That's called hysteresis. And one more bad guy. I'm just going to use some examples here, so you know, it's not bad when you take it apart. The definition of I is flowing in that direction. So let's look at the charging here. And what we see here is when our input waveform goes to 10 volts, as the capacitor asymptotically approaches 10 volts like before. And now what we want to do is find out what the current looks like. Well, okay, so let's begin. When V goes to 10 volts, VC equals 0. So this guy jumps up to 10. This is 0 volts. So the current flowing is going to be I equals 10 volts over 10K. If this is 0 and this is 10 volts, guess what? KVL says that voltage has to be across a 10K resistor. And our current then is 1 milliampere right there. Now the rest of this is Ohm's law. When VC is charged to 3 volts, so now it's gathered some charge here, it's 3 volts, the voltage across the resistor has to be 7 volts. 3 plus 7 is 10. So, again, solving for current, what we end up with is 700 microamperes, and that would be this point right here. There's 3 volts, there's 700 microamperes. Doing this one more time, when VC charges to 8 volts, well, there's 2 volts left across VR, and what we see is that I is equal to 2 volts divided by 10K, which is 200 microamperes, and that would be 8 volts here and 200 microamperes there. Not too bad. Now let's look at the discharging here, and this would be number 2. That would be this guy. And in this case, VC is going to be equal to 10 volts. Why? Because it charged to 10. And the source now is dropped to 0 volts. So, when the capacitor now sitting at 10 volts, and let me put polarity signs on this real quick, plus and minus, is that you have to realize that the internal impedance of the voltage source is 0 ohms. Very important concept. And the capacitor will now discharge through the resistor and across the 0 ohm source, which is at 0 volts. So it's the voltage C which is going to be driving this, and the discharge current is opposite to the definition of the charge current. So if we look at this, in part D here, we're looking at T0 plus, which is going to be now here. Source voltage is 0 volts. That makes sense. DC is 10 volts, fully charged. I is going to be 10 volts divided by 10K equals 1 milliampere. And since the physical current flow is opposite to the defined current flow, what we get is a negative 1 milliampere. Another example, as we work through this, at VC equals 4 volts. Now, the capacitor is decayed to 4 volts, which would be maybe here. What would the current be? Well, the voltage across the capacitor is the same as the voltage across the resistor. This is a short. I'm going to keep saying that. Internal impedance 0 ohms. I'm going to keep saying that too. So I would be equal to 4 volts divided by 10K, 400 microamperes, and then I'm going to put that as a negative 400 microamperes, which would be right here, corresponding to 4 volts on VC. And then finally, when VC equals 1 volt, VR equals 1 volt, short circuit, internal impedance 0 ohms, and that gives us 100 microamperes, since this is discharging, flowing opposite to the defined current flow. That would put us at this point right here, and this would be 1 volt. So, what we can see is we can find this, and when you think about what's going on with regard to the step voltage, now the energy stored in the capacitor is the guy that's taken care of the current flow, and here you see the decaying exponential is the cap discharges through the resistor, and this is the guy that's dissipating power. Energy stored in the capacitor as an electrostatic field. Okay, current example, and then that'll be the end of part 1 here. I'm going to analyze this as part 1 again. And what we want to do is find find I at t equals 4 milliseconds, and this is going to be, the current here is going to be an exponential decay, and I've not put the actual voltage in here to kind of simplify things a little bit. And since this is a decaying exponential, is what we have is the simpler formula of I initial times e raised to the negative t over time constant. So again, what's going to happen is that the initial is going to be multiplied by a value that's getting smaller and smaller and smaller. So the initial current here is going to be 1 milliampere, because that's what we had charged the cap to, and then as the cap voltage approaches 0, the current decreases. And when the cap equals 10 volts, well, what's the voltage across the resistor? 0. 10 volts here, 10 volts across the capacitor is 0 volts at the end, 0 amperes at the end. So as VC reaches Vs, the current approaches 0. So we want to find I at t equals 40 milliseconds, and we do this guy, and what we see is that's 162 microamperes, so that would be the point that it decayed to. And now if we take a look at number 2, and we want to find I at say t equals 1 millisecond, is that this is going to be, again, where the physical current is flowing opposite to the defined current. Everything is true as before. I initial is going to be negative 1 milliampere. And why? And that's because the voltage of the source just switched negative. And in doing so, we end up with a negative 1 milliampere. And applying this here equation to it is what we see is that the current flow in the capacitor, and for that matter, the whole circuit, is going to be 634 microamperes at 1 millisecond. So the voltage across the resistor is basically I times R. And as you can see here, if you understand the waveforms and when to use the charging waveform and when to use the discharging waveform, is a problem decomposes basically into Ohm's law. So that's the hardest part of this. Now, charging when VC initial is not 0 will be part 2 of this. I think we covered quite a bit here, and need to look that over. This is a little bit more involved, and this would be a circuit that's driven by bipolar square wave. Goes in both directions. So anyway, with regard to part 1 here, thanks for watching.